Hello and welcome to this lesson on reaction pathways. In today's lesson, we will learn how to calculate the atom economy of a reaction. We will also begin to understand why a particular reaction pathway is chosen to produce a specified product based on factors such as atom economy, yield, rate, equilibrium position, and usefulness of byproducts. So far, we've discussed how to calculate atom economy and percentage yield. These concepts help us understand the efficiency of a reaction in terms of the proportion of reactants that become useful products and the proportion of products obtained compared to the theoretical maximum. Building on this foundation, today's lesson will advance our chemical understanding by exploring how these calculations and concepts influence decisions on why certain reactions are chosen over others in industrial and laboratory settings. First, let's recap atom economy and percentage yield. Atom economy measures the efficiency of a reaction in terms of how well it uses the atoms in the starting materials to form the desired products. It is calculated using this equation: mass of desired product divided by sum of masses of reactants times 100. Percentage yield, on the other hand, compares the actual amount of product obtained from a reaction to the theoretical amount that could be produced if everything went perfectly. It is calculated using the equation actual yield divided by theoretical yield times 100%. When manufacturing a product in an industrial setting, scientists usually consider more than one reaction that can produce this product. Atom economy and percentage yield are two factors that affect the reaction pathway. Let us examine the factors in more detail. Firstly, higher atom economy means a more efficient and sustainable reaction, so reactions with higher atom economy are typically preferred. Next, the yield is the actual amount of product obtained from a reaction. Even a reaction with high atom economy might not be preferred if the yield is low. How quickly a reaction reaches completion is also crucial, especially in industrial processes where time is money. Faster reactions are generally more desirable. Rates of reactions are discussed in more detail in a later unit. Furthermore, in reversible reactions, the position of equilibrium affects the proportions of reactants and products. A favorable equilibrium position can maximize the production of desired products. Think of it like a balance. If the balance tips towards the products, you get more of what you want. This is discussed further in a later unit. Lastly, if byproducts can be used or sold, they can offset the costs, making a reaction pathway more economically viable. Choosing the optimal reaction pathway requires a balance of all these factors. For example, while atom economy is important for sustainability, it might be necessary to compromise slightly if a reaction pathway offers a significantly higher yield, faster rate, or more useful byproducts. To help us learn about reaction pathways, let's consider the industrial production of ethanol. This can be done via two pathways. Pathway 1 is the fermentation of glucose, which we've seen in the previous lesson. Pathway 2 is the hydration of ethan. We can calculate the atom economy for both of these pathways. Let's focus first on pathway 1. C2H5OH has a relative formula mass of 46. Since 2 moles of it are produced, the produced mass is 92. The mass of reactants, that is, the mass of C6H12O6, can be calculated to equal 180. Therefore, the total atom economy is 92 divided by 180 times 100, which approximately equals 51.1%, as we found in the last lesson. Now, let's work out the atom economy for pathway 2. 1 mole of C2H5OH gives a mass of 46. The total reactant's mass is the sum of the mass of C2H4 and the mass of H2O, leaving us with a total of 46. The final atom economy is 46 over 46 times 100 equals 100%. We can see that based on atom economy alone, pathway 2 is more efficient. However, scientists do not make a decision based on this alone. In terms of yield, hydration of ethene typically has a higher yield compared to fermentation. Furthermore, in terms of rate, hydration of ethene is faster than fermentation. On the other hand, hydration of ethene is reversible, and conditions need to be optimized carefully to push the equilibrium towards ethanol. Also, ethers must be sourced from crude oil, which involves complex and sometimes environmentally unfriendly processes. This illustrates that such decisions cannot be made on one factor alone, and chemists need to consider all the discussed aspects collectively in order to select pathways that maximize efficiency, sustainability, and economic viability. In today's lesson, we recap the calculations of atom economy and percentage yield. We then use these to understand several factors that influence the choice of a reaction pathway for producing a specified product. These factors include atom economy, yield, rate of reaction, equilibrium position, and the usefulness of byproducts. By understanding and optimizing these factors, chemists can design more sustainable and efficient chemical processes.